Okay, everyone, shall we start?
It doesn't work, so.
Oh, so sorry about it. Okay, so at least the
Maybe if I do this, maybe.
okay. So we have our own Origin Seminar organizer speaking today, Sebastiaan Haffert. He's been last time I checked email, it was summer of 2020. So Sebastiaan has been here with during the whole pandemic time when we changed the Origins to hybrid methods. I really appreciate all he's done. And it was Sebastiaan Krijt who recruited Sebastiaan Haffert, same Sebastiaan. And then at that time, it was a lot of work. And I really would like to appreciate it. So now, intro about Sebastiaan. He did PhD in Leiden in 2019. And he moved here and he was NASA Sagan Fellow. And after his 5 years here, 5 years, he's going back to Leiden as professor. So that's a wonderful news. And okay, so Sebastiaan's main interest is developing astronomical instrumentation, especially adaptive optics and to characterize and observe exoplanetary systems. So adaptive optics, chronography, and high resolution, even spectroscopy using MagAO-X. That is really awesome. And now I finally start collaborating with Sebastiaan. And it's really, it has been wonderful to have him here. And of course, he's a PI of the wonderful VisX, the visible infrared field spectrograph extreme that I'm really fond of using now. So now I would like, Jared, would you like to add more fun introduction?
Sure. Well, so as you just heard, Sebastiaan's leaving. I just counted, there's 15 days left. His presence in Tucson. He's in such a hurry to leave, he's not even going to come on the next MagAO-X run, which starts about then. I think the talk you're about to see is going to be the real culmination of some amazing work that Sebastiaan's done. When we conceived of MagAO-X, a lot of this science is why we wanted to do it. But sometimes you got to get lucky and get the right people to show up and help you figure out how to do it. I think you're going to see that Sebastiaan has really laid the groundwork for what I think is about to become a really amazing time in exoplanet imaging, especially as we pursue reflected light imaging. Because of Sebastiaan's work, we're closer than we've ever been closer is what our project manager likes to say. So anyway, congratulations, Sebastiaan, on that great 5 years here on that upcoming job. And I think the exciting thing is that we have a super clear understanding between us. Sebastiaan's going to continue to be part of MagAO-X, collaborate. We're not going to erase his SSH keys. So we're going to be hearing from Sebastiaan at MagAO-X a long time into the future. So, Sebastiaan.
Thanks for a wonderful introduction. Yeah, like Serena said, and Jared, I spent 5 years here at Steward Observatory. So I'm going to talk a little bit and reflect a little bit about the past 5 years that I spent with MagAO-X and all the work that we did. I cannot cover everything, of course. So some things have been cut, some things have been, but it's a selected features. Okay, so of course every exoplanet talk has to start with this figure. I updated the number of detected confirmed exoplanets, which is about 5,600 now. But most of these planets have been detected by transits, so transit observations with Kepler tests and ground-based instruments. And then another 1,000 or so through radial velocity. And currently direct imaging we have about 70 planets, which is more than 5 years ago. 5 years ago, it was only like 20 or 10. So the past 5 years, there's been a pretty big increase in the number of directly imaged planets, actually. And later in the talk, I will come back why that is, or why I think this happens. So as you can see here, direct imaging, all those planets are in the top right. They're all massive planets. They're all Jupiters, and they're all at large orbital separations. And that's because it's at the moment very difficult to go close in and to go to the lower mass planets, which is why we need to do all this technology development. We want to push inwards and to lower masses. So I would do a very quick recap of high contrast imaging. One of the most important things is the diffraction limit. So on the left, you can see an aperture telescope, and on the right, the PSF pattern that it generates. And then if we do like rough estimates, then for current telescopes at 750 nanometers, so at visible wavelengths, you get a full width f-max or a resolution of about 16 to 24 milliarc seconds. With our next generation of extremely large telescopes, such as the ELT or GMT, we will be able to push this resolution down to 4 to 6 milliarc seconds, so really high resolution. So we need this resolution because we want to search for planets. They are at short orbital separations, small angular separations. And another thing that's challenging is the contrast. So here you see a cut through of that PSF that I just showed. And contrast is defined as the ratio of the peaks between the two PSFs. So here I'm showing a planet that's injected at 5 times the diffraction limit at 10 to the minus 8. So a contrast of about 100 million. However, if you look at actual spectra, we can see that contrast changes. It depends on the type of atmosphere, it depends on the planet size, it depends on the orbital separation. It also depends on the wavelength that you're looking at. So contrast depends on a lot of things. But in general, for a sun-like star and for an Earth-like planet, we need a contrast of about 10 to the 10. So 10 billion. It's pretty tough. So to get this spatial resolution and the contrast, we use direct imaging instruments or high contrast imaging instruments. And here you can see a schematic of such an instrument. So often-wise, direct imaging telescopes or direct imaging instruments start with a large telescope. And luckily, hopefully we'll get a couple of them. We will have the Extreme Large Telescope and the Giant Magellan Telescope. Well, we'll hear about that, I guess, later this week. if GMT will, they will do something with GMT. And then the next step is adaptive optics, because most of these large ground-based telescopes are on Earth. They image through the atmosphere, so you need to counteract the effects of the atmosphere. So here on the right, you can see an image from MagAO-X where you see the atmosphere, and then you turn on the AO system, and then you can see we close the loop. And we have a very sharp image. And then after we close the loop, you can actually see the companion here, which is a BiPAP B, which you couldn't see in the seeing limited images. All the other structures that you're seeing are instrumental artifacts. But this one Speckle or this one PSF here is real. So because planets are super faint, we want to get rid of as much starlight as possible, because starlight is the thing that is really that causes the noise. So we use coronagraphs to block starlight. So on the left, you have the input PSF, and on the right, you can see that after a coronagraph, a lot of this diffraction structure is gone. So the only thing that's left are wavelength errors that pass through the coronagraph, but the constant diffraction factor is gone. And then finally, because there's still light that leaks through the coronagraph, you need to use advanced image processing methods to disentangle starlight from actually astrophysical sources. So here, for example, you can see there's a certain sequence. You can see the hints of the disk in the raw images on the left, but it's very difficult. So if you use something like angular differential imaging or something more advanced, you can actually recover things like circumstant disks and faint planets. So in the end, it's this whole picture for high contrast imaging that needs to work. You need to have large telescopes, you need to have adaptive optics, coronagraphs, and post-processing techniques. And all of these really need to work very well together. So that's why I like doing high contrast imaging. There's a lot of things to develop, there's a lot of things to do. So when I got my PhD back in 2019, I actually moved from the Netherlands over here to Tucson, which is roughly there. And then why I moved to Tucson It's not because Tucson has amazing nature or has very fun cacti or has good food. I moved here because MagAO-X was built here. So MagAO-X is well, I cannot say a new instrument anymore now, right? I mean, it's already been operational for 5 years. So MagAO-X is a high contrast imaging instrument for the Magellan Clay Telescope in Chile, Las Campanas. And MagAO-X is working very well now. So here you can see some highlights where we are actually doing science with it instead of it just sitting here in Tucson. But this is the reason why I moved. So in late 2019, MagAO-X was on the NASMET platform for the first time. And we got the first light image. So this was the very first, one of the first PSFs that MagAO-X made with a strail of about 46% in C prime. And we were very happy with it. I say we, I wasn't there because I wasn't on the run because I had to fly back to the Netherlands. Because during the run, I was actually getting my thesis, my PhD. So I didn't do my, I didn't join that run. But I thought, we'll be fine. A couple months later, we'll have another run. But that didn't happen because COVID happened. So MagAO-X did not go to the telescope. But luckily, we just shipped MagAO-X back just before everything turned bad. So MagAO-X was here in the lab and I couldn't observe. And I came here with my fellowship, with my second fellowship, to use MagAO-X for observations. So I had to rethink and re-strategize what I was going to do. So what we actually want to do with MagAO-X is we want to go after ProcSat B. Proxima Centauri b. That's really one of the key science drivers for MagAO-X. And that planet, that's the pink one here. So here you can see, as function of angular separation and contrast, a whole slew of planets. The triangle or the gray symbols are reflected light planets, and the red ones are thermal infrared planets. So you can see thermal infrared planets farther out, much brighter, much easier. We can do that. We can see them. It's not super difficult. We can do that now. But reflected light science, there's a pretty big gap between what we currently can do, which is this contrast curve here, this sensitivity curve, versus what we want with MagAO-X. So this is the improvement that we want to gain by doing more R&D. So what causes this gap? And this gap is caused by speckles. So here you can see a video of HR8, HR8799. And you can see there are 4 planets in here. They're orbiting their host star. And for all the different frames, you can see the different speckle patterns that appear. And these speckle patterns are actually the fundamental limiting noise source for high contrast imaging. It's these speckles. They're very annoying. And they're causing all sorts of trouble. So it's actually, this is something that we discussed internally in MagAO-X group, and Jared also discussed this last year at ELT. But what actually sets the fundamental limit for high contrast imaging? So we often talk about contrast. Contrast is not very well defined. It's a metric. Depending on who you ask, you get a different number. And it has several meanings. Like you can say astrophysical flux ratio between the star and planet, but you can also say the contrast that your instrument is achieving. And it also does not tell you how well the instrument works and what your signal to noise is, because contrast is not a noise model. So if you assume like you have a perfectly static background, it's actually pretty easy to get very high contrast. Because if you have static backgrounds, you just remove that static background and you're done. And you can see very faint objects. So suppose that we're in the photon noise limited regime. So if that means you have completely uncorrelated photon noise, which means that the only noise source is just the total number of detected stellar photons at the location of your planet. And due to the large contrast ratio, the photon noise from the companion itself does not really matter. like photon noise from the planet is so small compared to the photon noise from the star that only the photon noise of the star is really important. So in that regime, you can do a very simple signal to noise calculation. It's just signal divided by just planet photons divided by stellar photons. Then you can fill that in for a typical number. And you can see if we have a static background of 10 to, of a, like if the star creates a static background at a contrast of 10 to the minus 6, and the planet has a contrast of 10 to the minus 10, so that's an Earth-like planet. And then we use some typical values for a sun-like star. And you can see that in 60 hours, you can actually integrate through a static background. So the contrast is not really a problem here. Even if we make the planet fainter, we just integrate for longer and we'll still detect the planet. Contrast is not a problem. What is the problem is the spatial and temporal correlations that you see in the speckles. That's actually the problem. And it's not the speckles themselves. So if you do actual more extensive simulations, some more realistic simulations, then you calculate what's the variance as function of exposure time. Then you can see that this variance does not immediately scale as square root t, as you would expect from photon noise. So if you have uncorrelated noise scaling, it would just go down with square root t. However, these speckles have a certain lifetime. So it takes several milliseconds to 10 milliseconds, or maybe even like multiple minutes before the speckles become uncorrelated. And it's only when you have uncorrelated patterns that statistical averaging actually helps and that you can go deeper. So you need to have statistical averaging. And it means you need to take into account lifetime. And here you can see that we are actually, this lifetime actually has a huge impact on the timescales that you need to reach a certain sensitivity. So first of all, we have a huge gap here from simple adaptive optics control and optimal predictive control. So there's already an order of magnitude that we lose in sensitivity if we don't do perfect control of our AO system. But the speckle lifetime itself also creates like 2 or 3 orders of magnitude of sensitivity loss, just because we need to wait before the speckles have evolved enough to get a new uncorrelated pattern. So theoretically, if we could reach the photon noise limit of our observations, we would actually be 1,000 to 10,000 times faster than we would be now. So this is a huge problem. So it's all about speckle strength and its lifetime. So in our challenges, these are sort of the 5 big things that we need to do. We need to control these speckles on sky. We want to get rid of them. We need to apply predictive control. So we want to get more advanced waveform control to push these contrast curves down so that we have a better starting point for the statistical averaging. Our systems are not yet operating at the fundamental limit. So that means that there are still ways that we can change the optics and the hardware to increase sensitivity without doing weird stuff. And then the 4th one, it would also be great if we can actually model speckle patterns and we can actually subtract everything that we know is stellar light from the images, because then we can actually achieve the photon noise limit instead of just this speckle noise limit. But it's very complicated. And the 5th point, which is also crucial, is we don't have ELTs yet. So we still need to wait about 5 years or so for the first ELT to have first light. So we have lots of work to do, but I think the potential of high contrast imaging from ground-based telescopes is really, really big, especially with the ELTs. So we should spend a lot of effort and we should put in a lot of work to actually make them operate at the fundamental limit, because then we can do very interesting things. So then we will be able to go from this current goal of what we do with MagAO-X to the goal of the giant segmented mirror telescopes. Then, as you can see, will be maybe 1 order of magnitude less sensitive than space-based telescopes. But even with that, due to the smaller inner working angle of these large mirrors, we can do way better, or at least not way better, but we have access to like a larger population of planets, I think, than space-based telescopes. So that development costs a lot of time. It's very complicated. And that's why I think MagAO-X is really crucial, because we ship it back and forth between Tucson and LCO every time, or not every time, but often. And every time we ship, we can actually improve the instrument. We can improve its performance. We can add new chronographs. We can add new sensors. We can add new science instrumentation backend. And it's this cycle of shipping back and forth and improving things is really the agile approach that we need. If you deliver a facility instrument to many observatories work with facility class instruments, so that means you deliver it, and then it's owned by the observatory, and then it's very difficult to change because you need to go through a whole process actually to change the instrument and optimize it. And because of that, the technology development in the lab is actually going very rapidly. We develop a lot of new stuff in our labs, but actually implementing it on Sky, there's a huge delay because every time we need to go to these facility instruments and then we need to try something, and that's very difficult. That's actually the one thing that blocks us the most is that step from lab to on Sky. But however, with MagAO-X, because of this agile approach, we can actually do instrument development like they do software development very fast. And very few platforms allow for this. So MagAO-X are especially for AO platforms, like AO instruments. There are currently only, I think, 3 instruments in the world that can do that have this agile approach, of which MagAO-X is on one of the bigger telescopes. So I've talked a lot about MagAO-X, so now I'll show it for people to have a bit of a feeling for what it is. So MagAO-X consists of 2 optical benches. On the top bench, we have all the adaptive components that do adaptive optics correction and atmospheric dispersion control. And then on the bottom, in this block, we have our waveform sensor that controls our AO system. Then we have our science instrumentation, or, well, our chronograph. In the middle bench, we have the chronograph. And then on the left, we have our science instrumentation, which has expanded quite a bit over the past 5 years. So MagAO-X only started with 2 cameras, and now we have 3 science backend instruments with 2 more planned. So we're expanding to a lot of different, a wide variety of science cases that you can actually do with MagAO-X. So we have MagAO-X. So now we are going to tackle the problems. So we have rapidly changing atmosphere. That's one of the issues. So you have the atmospheric turbulence. So even with a high-speed AO system, the turbulence still evolves so fast that we cannot always catch up. That means we're always lagging behind, leading to atmospheric speckles. So those are the atmospheric speckles. Then we have the slowly changing instrument errors. So here in the middle, you can see this is a chronographic image. And in principle, it should be completely dark because the chronograph should remove as much light as possible. But due to imperfections in the instrument, we see these instrumental errors. And then when we go to the giant telescopes, we actually get segment phasing errors. We actually have issues with that. We have these large mirrors that walk out of phase. So during my lab time, or like my COVID time here in Tucson, I mainly focused on just implementing new optics and new algorithms on MagAO-X to tackle each of these 3 problems. So that was actually my first 2 years. And then after we were able to tackle those problems, or at least after 2 years, we were allowed to go back to the telescope again. We're extremely happy. So here on the left, MagAO-X has been put in a box in a truck, and it's on its way to the airport. In the middle, you can see MagAO-X very happily in LCO. We're bringing it to the telescope, and on the right, we're actually installing it on the telescope. So this was our first run back again in 2022A. So here is the team that installed MagAO-X, and we're very happy that we're at the telescope. I have to say it was a bit of a strange run because we were actually the first visitors to LCO after COVID. It was an interesting experience. As I showed before, MagAO-X works really well. We now have diffraction limited imaging at Z-band. because of the upgrades that we did, we actually increased our strail at Z prime from about 40% during first light to about 70% in what I call in 2022A. So there's a huge improvement from 40% to 70%. But we were still not really at the design level. So the design for MagAO-X was 90% strail at Z prime.
How many error rings did you count?
Well, it goes all the way out to the control region, so that's 24. So our control region is roughly 48 lambda over d. So here we are working at the telescope, doing a lot of work. It's very complicated, but luckily the observatory helps us by supplying a lot of empanadas. Yeah, so there's a thing in the LCO where every Sunday you can get empanadas. And whenever we come, we have a pretty large team because we usually come with between 8 to 10 people. And we all usually order 4 empanadas per person. So there's usually a huge mountain of empanadas every Sunday. So one of the residual errors after the AO correction is really the instrumental errors. So we upgraded MagAO-X with a new DM. So on the top edge in the purple circle, you can see our DM for the atmosphere control. But then in the green circle in our chronograph, we actually added another DM, which is separate from the AO DM. And this does corrections for all the instrumental errors. Reason why we did that is because it's actually quite complicated to otherwise compensate for instrumental errors. A typical AO system uses a wavefront sensor and then controls this atmosphere DM to get rid of the atmospheric speckles. And then you have your science camera, and then the science camera tells the pyramid wavefront sensor, hey, there's like a focus offset, or there are like errors in the system, and I want you to correct for that. But because pyramid wavefront sensors are quite nonlinear, if you offset them, they become very unstable, and it becomes very difficult to actually correct for these instrumental errors. So that's why we decided to have 2 different DMs. There's one DM that does the atmosphere and one DM that corrects for the instrumental errors. So we separated them, and that's also a good software engineering principle, is separation of responsibility. And that's what we applied here. And that worked really well. So this we applied a technique called focus diversity phase retrieval on sky. And it means we actually bring our system out of focus on purpose. And by bringing it out of focus, we can actually measure what's wrong with the system. And we can measure the instrumental errors. And here in this video, let's turn it on. You can actually see that sometimes we have a flash of defocus. And that's when we measure it. And then slowly, that was a flash of defocus. It's very quick. And we do that a couple times. And then every time we do that, we add that focus offset. We can actually measure the instrumental errors and clean up the PSF. Make it better. I don't know how long it's. So this is something we now do at the beginning of every observation. So we do 5 minutes or 5 to 10 minutes of this focus diversity phase retrieval to clean up the PSF and to make it really good. So this is actually something that's really difficult to do on sky with ground-based telescopes. Because if you want to do a focus offset, you either need to move your whole camera and your instrument, or you need to offload the focus to your wavefront sensor and your AO system. But that's also very complicated. So both of these options are very complicated, which means that this type of focus diversity phase retrieval, there are actually very few instruments that are able to successfully use it on the ground. Like James Webb uses this all the time, but that's a space-based telescope, and those are way more stable. It's easier. So here you can see the difference between before and after phase diversity. So I have to say that here we already did one on the lab internal source, so the differences are not too big. But if you look closely, you can actually see that there's an asymmetry here, like here the left side and the right side are not the same. Well, in the corrected PSF, you can see that the left and right side are similar and symmetric. Those are like residual wavefront errors that the algorithm cleans up. And now think I dare say that we're reaching at least an 80% strial Z prime. I'm not sure what the actual number is because we still have to reduce the data because this is data from 3 weeks ago. So we still need to crunch the actual numbers. But we're actually reaching performances that other instruments used to reach at IR wavelengths. So this is another way to show the improvement that we made in the last couple of years by adding these new techniques. This is an H-alpha PSF of PDS-70, which is a 10.7 magnitude star. And on the left, in 2022, we started with a strial of 9%. We're not even showing the images from 2019. And then in 2023, we achieved a strial of 20%. And then after adding this new DM and doing this new focus diversity-based phase retrieval, we're actually hitting 26% strial at H-alpha wavelengths for this for a faint star. I would say that's actually really good. We're within a couple percent points of the actual design, or well, it fluctuates a bit. Like it depends on the atmospheric conditions, but we're pretty much at the originally designed specifications of MagAO-X at H-alpha. So that's really good. I'm really happy with that. That also allows us to do like a lot of new novel science at optical wavelengths. Because the wavelengths are so short, other instruments usually don't have the performance necessary to image planets. But because we have this high performance, we can actually do visible characterization of brown dwarfs and companions. Here is WISES 1b, which is a large separation exoplanet in I-band and Z-band. And I think these are the bluest detections of this companion that have been made. And these observations were also the precursor to the Zumies survey that we're doing with MagAO-X. So I'm working together with Logan Pierce on this. And the Zumies survey is actually a survey to fetch companions around accelerating stars. So we're using Gaia and RV priors to pick objects with high likelihood that have a high likelihood of having an unseen companion. So if there's some astrometric or RV indication that we have a star that is moving in a weird way, then it might be due to a companion. So we try to search for them. And the WISES observations were sort of tests to see if we could actually have the sensitivity to detect them. I think they're...
Lair just answered.
Yeah.
That was a question. Thank you, Lair.
And I think with Zumies, we're actually quite successful. All the Zoomy targets that we looked at during the last run had a companion. So the priors that we selected were actually really good priors. So here's the first one, 1b, the separation of 125 milliarc seconds, contrast of about 7 magnitudes. There's another one at a separation of about 110. Contrast, I've not calibrated it yet, so I don't know. But it's also about like 6, 7, contrast of 6, 7. And that places these two companions in the brown dwarf regime. So they're not exoplanets, but brown dwarfs. But these observations, what we try to do with Zumies is to find benchmark brown dwarf companions. So one of the most important things for us in stellar astrophysics has been normal stellar binaries, because from stellar binaries, you can actually retrieve dynamical masses. That means you can actually get an absolute mass estimate of your stars. We know a lot of brown dwarfs, field brown dwarfs that are alone, but because they're alone, we can actually not measure their masses very well. Like to measure their mass, we need to use evolutionary models, but then you have a model-based measurement of their masses. And by using direct imaging plus RV and astrometry priors, we can actually measure dynamical masses to the percent level. It's extremely accurate. And with that, we can actually start to constrain the mass-luminosity relationship of brown dwarfs, which is important to constrain the evolutionary models. So that's why I think detecting brown dwarf companions is, I think, one of the big things that we need to do now that help us constrain these evolutionary models. And not only is this important for brown dwarfs, but also for exoplanets, because exoplanets are their evolution is very similar to that of the low mass brown dwarfs. So if we know how brown dwarfs evolve, we also have a better indication of how exoplanets evolve over time. So this is something that lots of people across the world, of course, do, because this is very interesting. So a lot of people do this dynamical mass estimates, luminosity. But it's important science.
So there is a question, but I wonder if Laird is working on it. Laird, let me know if you are working on it.
Yeah, actually, I
I
can just answer it or whatever.
Okay. So you can already see from these observations, if we want to detect exoplanets that are even closer in and fainter, it's going to be tricky because you can see the speckles around our coronagraph, or you can see the speckles at the inner working angle, like here and here. They create a bit of a mess, and these are instrumental speckle errors. So they change from minute to hour timescales, and if you want to average those out, you need to wait for like hundreds of hours. So the only way to really get rid of them is by using active control and using coronagraphs. So one of the coronagraphs that I've implemented on MagAO-X is called the phase apodized pupil DO coronagraph. It's a big acronym. But effectively what happens is that instead of having a circular focal plane mask that's pretty typical coronagraphs, is we have something called a knife edge. That means you mask one half of the PSF completely, and you pass through the other half. And that's effectively what we do. So we have the PSF that gets, or the pupil, it gets focused to the focus here. And then this focal plane mask, it masks like the bright side of your PSF. And it only passes through the coronagraphic side. And then if you add your Leo stop and you do a couple other things, you actually get a deep, nice dark hole, nice coronagraphic dark hole. And there are several advantages to this coronagraph. I think the first one is that it's a small inner working angle coronagraph. So you can actually look for planets at 1.5 lambda over d. So for MagAO-X, that means that we can search for planets at 45 to 50 milliarc seconds, which is really tight compared to other instruments. So here you can see one of that focal plane mask manufactured by Admiral McLeod, who was a master's student in our group. And then here you can see our coronagraphic image of that knife edge with MagAO-X. So this is lab data. So one of the things that you can see immediately, instead of a dark hole, we have a lot of speckles, and those are the instrumental errors. So during my COVID period, I developed a new waveform control algorithm that can actually get rid of those speckles. So if you actually turn it on, you can see that the instrumental speckles, they go away, and the only thing that's left is this halo of atmospheric speckles caused by the AO. So this is lab data. So last run, we were actually able to go on Sky and try it out, and it worked. So on the left, you can see all the quasi-statics before waveform control, and on the right, you can see the quasi-statics after waveform control. And you can see really in the white area is that a lot of these very bright speckles, they disappeared because we did this active control of them. We removed them. And it made a huge difference. For example, here we have the third companion from the Zumies survey that we were actually able to detect in a single exposure, and we didn't need to do any post-processing. So the speckles, so the coronagraph together with the starlight suppression techniques were enough for us to directly detect this companion at about 200 to 250 milliarc seconds. So detecting this companion itself was actually not super difficult because in the end, it was a star. We were hoping for a brown dwarf, but it was a star. So it was pretty bright. But if we look at the actual noise residuals, we were able to get a contrast of 10 to the minus 5 in a couple seconds, which is really good. So we are now working towards making this EFC algorithm, so this speckle control algorithm, something that's operational for everybody that wants to use MagAO-X, so that we can actually suppress these speckles and actually get high sensitivity very close in. And then that lets us to start to do actual high contrast close in exoplanets, because I've now only shown that it works on brown dwarfs. We have some preliminary data, of course. but I still need to reduce it because we counted how much data we took, and it's 2 terabytes for one target. So I have to do a bit of work to actually show the sensitivity curves. Yeah. So the last thing that I worked on, I mean, I've worked on many other things too, but last thing that I want to mention is on the science backend. So when I came here, MagAO-X only had cameras, so it could only do broadband imaging. And one of the things that I'm really interested in is spectroscopy. So I developed the visible integral field spectrograph extreme for MagAO-X. It has 2 different modes. So you can see a picture on the left. It's an old picture because the instrument actually looks different now. It has a box and there's a lot of stuff around it. But in principle, it stayed the same. Like performance-wise, it became better, but parameter-wise, it has high-resolution mode to do spectroscopy of emission lines. So you put in a specific emission line filter, and then we can take narrowband spectra at high resolution, or you go for a low-resolution mode, and you can do broadband characterization. So you can do a trade-off between what you're interested in. I added the emission lines because I'm very interested in things like disk winds and jets and planetary accretion. So I really want to study things like the oxygen lines and the H-alpha line at high resolution. But if you want to do reflected light characterization of planets, then you need to have a low resolution broadband mode to get albedo measurements. So there are different modes for the spectrograph. At the moment, the high resolution mode is the only one that I've really commissioned and have produced data for. For the low resolution mode, I've taken the first on-sky data sets last run. So I cannot show any results for those yet because it takes some time to reduce the data. But for the high resolution data, I can actually show you because I've been using the high resolution mode for 3 semesters now, 4 semesters. So with MagAO-X, we get high spatial resolution because we're diffraction limited. And with VisX, we're actually sampling the PSF with 7 milliarc second pixels. So we are taking 7 milliarc second spatial pixels. And we have a spectral resolution of about 15,000. So delta V of 20 kilometers per second. And here you can see an image of Betelgeuse that was taken with VisX. We can look at H-alpha, we can look at continuum, and we can see that there's a difference between H-alpha and the continuum. And then if we actually measure the equivalent width for every pixel, and we measure the velocity, we can actually see that we can actually reveal the photosphere of Betelgeuse together with the circumstellar environment, and we can actually measure the velocity of the winds that Betelgeuse is releasing. So this is one of the first observations that I did because Betelgeuse is super bright. And these were done in our infamous 2022B semester, where we had horrible seeing. And the only thing we could look at was Betelgeuse, pretty much. Another object is our Aquarius, which is an interacting binary system, where there's one star that donates mass to the other star. And you can also see in the imaging mode, we see these huge, nice jets that these two outflows that these 2 components create. And then if we zoom in with VisX, we can see the 2 companions. And we can also see that there's a jet. It's a little bit faint, but you can see the start of the jet here. And due to the high spectral resolution, we can actually start to velocity resolve the 2 components and start to constrain the kinematics of the interaction and the orbit. So this is the original purpose that we built, that I built VisX for this type of science, but then on planets and stellar outflows instead of interacting binaries. I had to do some work to improve the sensitivity for VisX. So from 2022 until 2024, we actually did multiple upgrades to increase sensitivity, and we're now finally at the level where we're actually reaching the limit of the Saturn. So here you can see HD 142527b, which is a star. Well, this is not B, this is A. B is hidden. B is an M-dwarf companion to the star that is accreting, but you cannot see it in the PSF image itself. But if you do some spectral differential imaging, you can actually reveal the close-in companion at 50 milliarc seconds. And if you look closely, you can also see that there's still some residual around the star. And that's not speckle noise. That is what I think is is maybe an outflow that's generated between the two stars from their interaction, because there is still some stellar disk material left. So there's a lot of gas and dust that can be injected. And then if we look at the spectra from these two, so on the left, it's the spectrum of the primary, and on the right, we see the emission line of the secondary. They're actually different if you look at it. It's a bit difficult due to the scaling, but on the left, we have a broad emission line with asymmetric absorption. This one's also very broad and plateaued, while the companion has a very peaked emission line. So we can actually now do emission line sensitivity studies on accreting companions. The next goal is actually, I took data also of accreting protoplanets, but I'll have to figure out if I reach sensitivity. And our next step is actually to bring MagAO-X in some sort of shape spiritually to the Giant Magellan Telescope. So GMT, of course, will have a much bigger aperture. That means we can access more planets. So a lot of the work that we're doing is actually in development for GMT. So this is artist impression. At the moment, GMT is a hole in the ground. It's a very nice hole. You can visit it if you go to LCO. But this is Giant MagAO-X, or GMagAO-X, we're developing. So last February, we actually had our preliminary design review, which we passed. And GMagAO-X is going to be the spiritual successor of MagAO-X, but then for GMT. And it's going to be a huge upgrade. It's going to be a lot of work to get this done, but we have another 10 years or so. We are aiming to become a first light instrument in 2031 or 2032. So hopefully 10 years from now, or 8 years from now, we'll have GMagAO-X, which will be able to do this high contrast imaging science on the GMT. And I think I can show how much of an improvement it will be. So these are images that Lair took of PDS-70, which are creating protoplanets in Agile. And this was roughly 2 hours of data. With GMT and GMagAO-X, we can actually do the same thing, but then in about 1 minute. So 1 minute of GMT time is equivalent to about 2 hours of Magellan time. And not only do we get equivalent, well, it's not equivalent, it's way better. So we should really build GMT and GMagAO-X to do this type of science, because you can see how much of an improvement it makes. So in conclusion, MagAO-X is on Sky. We're doing science with unique capabilities that no one else has. It's an active development platform, which is really important. And due to this agile approach, I think we are actually on our way to start doing reflected light imaging in the next couple of years. So I think MagAO-X is proving to be an excellent pathfinder for GMT. And sadly, after 5 years, I'm leaving. I'm going back to the Netherlands. But I'll keep in touch. Thanks for that.
Thank you, Sebastiaan. So now it's time for question.
Really exciting. I was just wondering, you showed the spectral differential imaging enhancing the contrast. Could that be used with, say, an H-alpha observation as well to increase contrast over just a filtered imaging observation?
Yeah, so that's the goal, to go to this high resolution. Because if your source is spectrally unresolved, you gain in signal to noise until you start to resolve your emission line. And we expect planetary emission lines to be very narrow, because planets are not super kinematic or anything. So we expect them to be like on the order of 20, maybe 25 kilometers per second. So I matched my resolution to the expected width. So that's why if you look at these narrow bands, we expect there to be a contrast enhancement, because we don't capture all that continuum light from the star.
Okay, Justin?
Yeah, so you mentioned the two different IFUs that you have. Is there a plan to do spectroscopic characterization of those new Zumies companions, or is that?
No, I took data of one, but I still have to reduce it. So,
Do you have
yes.
a question?
Yeah, you mentioned predictive control for speckle removal.
Yeah.
So what is the idea that I just wanted to know a bit more about that?
Oh yeah, I skipped over that because of time constraints. Yeah, I actually don't have slides here to show that, but yeah, so that for predictive waveform control, what we try to do is we try to go from the bottom image to the top image for all conditions. So on the top image, you can now see a typical on-sky observation if you have an atmosphere that's very stable, that doesn't evolve very fast. So sometimes you just have these nights which are really good where the atmosphere doesn't do anything. But then sometimes you also get nights where the atmosphere is just decided like, okay, let's have a jet stream. We're going to blow a lot of wind across the telescope. And then you get images like on the bottom, where you see this huge asymmetric, we call it butterfly effect or wind-broken halo. So this is all just because the AO system, we take a measurement, we measure what the turbulence is, and then we send a correction to our deformable mirror. But in the time that we take the measurement, we calculate what we need to do, we send it to the atmosphere has changed. And because of that, there's this catch-up effect. So for predictive control, what we try to do, we try to use models. And you can choose your favorite model that tries to predict what the atmosphere is going to do in the next couple milliseconds. And instead of sending a control command that depends on what you're measuring now, you're going to anticipate what's going to happen in the next couple months. So you're sending an anticipated command. And that should bring actually, if you are in conditions on the bottom, you should be able to go back to like the quality of the top one using predictive control. But it's very difficult because
Yeah, how good are these models?
so that's one of the big issues, is that we don't have really good models for this type of work. That means that in the past 30 years or so, model-based predictive control has not worked super well. So now the past couple of years, we're actually changing towards data-driven predictive control, where we try to use the data to create predictive models. And that seems to have somewhat more success, but it's still difficult.
Thanks.
Dominica?
What's the limited magnitude for the MagAO-X, and also what's the predicted or designed limitation for Giant?
So it's for both of them sort of the same thing. It's 11th magnitude in I band. That's for the visible waveform sensor. MagAO-X is also probably going to get an infrared waveform sensor. And then that means the limiting, so depending on which of the two you choose, you can also have a limiting magnitude of 12 in J or H. So it depends on what type of, like which sensor do you choose to do your waveform sensing with. The problem is like if you use H-band light for waveform sensing, you have less light for science. Because you need to choose how to split the light. So either you send light for the waveform sensing or you use light for science.
So you can use like I-band for the waveform sensing.
Yeah, I mean, there are more complex trade-offs and better filters that try to do things. We're still deciding how we're exactly in which ratios we're going to split light. So that's a in progress trade-off.
So far, it's then, as of now, which one is the best wavelength to use for the waveform sensing? If you want to do H-alpha.
For H-alpha?
Yeah.
Probably J-band.
Mm.
Because a lot of the H-alpha protoplanets are around T-Tauri stars,
Right.
which are often very red and faint.
And the brighter J.
And then brighter in the red than in the blue. But MagAO-X only has a visible camera, so we're limited to I-band.
Yeah.
We want to upgrade to also include J-band waveform sensing in MagAO-X. Because, for example, in PDS-70, it would double our trail. We will double from like 25% to 50% if we were able to do J-band waveform sensing.
Is there any plan for the upgrade?
We have a plan, was not funded. So we just need to
I don't
wait
think
for
it funded, yeah.
grants.
Okay, any other question in the room? Oh, yeah.
Yeah, you mentioned about horrible seeing. What was the what was the frame rate you used?
Oh, like that was one semester 2022B, where the seeing was consistently above 1.5 arc seconds. So it was between 1.5 and 2.5 the whole run. And that's outside of the stroke of our DMs. So it didn't even matter how fast we ran the DMs. There was just not enough stroke for us.
Okay, from online audience, do you have any question? Please raise your hand. I mean, there's a comment. Great talk and excellent work over the past years. Sebastian, thank you. And I bet best of luck in Leiden. That's a comment from Daniel Pai. Okay, any other question? Online? Here? All right, then thanks, Sebastian. And I will see you next week.